Okay, so today's going to be a fairly short little lesson. It's our introduction to our new unit of solutions. This whole unit is about everything that you can think about happening in water. You guys having fun back there? All right, focus on me. So, starting out with solutions, we're going to first take a look at the dissolving process. So in this picture, you have a salt, specifically this could be a representative of sodium chloride. I don't think it says anywhere exactly what kind of salt this is, but we do know the salt has a cation, that's a positive one, and the anion, that's negative. So it could be a couple things. What else could it be if it's not sodium chloride? Barium chloride? Could it be barium? No. Potassium chloride or potassium fluoride or anything in group 1 with any halogen, right, as ions. Now, what goes on in the dissolving process? And there's a lot of debate about these ionic bonds that exist between the actual ions. But what happens is, due to the fact that water is of a certain polarity. Tell me about water. What is water? Water is? It's a polar molecule. So if we have water, we'll say that's the oxygen. And then we have, I have to color it in now because I'm obsessed about it. And then we have some little hydrogen ions on it. Not ions, my bad, hydrogen atoms. We get a polar molecule due to the super high difference in electronegativity between the oxygen and the hydrogen. So oxygen is pulling all the electrons in this molecule towards itself. Now it's not stealing hydrogen's electrons. The bond is still a covalent bond between these two. But because of this, we get a little partial charge on the oxygen side of the water molecule. To indicate partial, we use this little lowercase delta. And what is this partial charge? Positive or negative? Electrons are being pulled toward it, guys. Positive or negative? Negative. How can being surrounded by electrons make you positive? No. Electrons are being pulled this direction. All right? So, for instance, I'm holding a pen for those of you at home, and Irene's going to grab the pen. In that pen are 2 electrons that we're bonded with. Okay? She is going to be more electronegative than me. She's oxygen. So what is she going to do? Pull that way. So electrons are closer to her, so she's kind of partially positive. What am I, a little hydrogen out here? I'm sorry, I said it backwards now because I'm thrown off. She's going to be partially negative because she has electrons closer to her, so I am partially positive. Okay? We're still sharing, but I'm partially positive. So the hydrogens are going to have a partial positive charge. Now, because the ionic bonds that exist between these ions is charge-based, a water could sneak in, and this portion of the water is what? This red part. Partially what? Partially negative, so it can sneak in and kind of get in between those ions due to its own partial charge. So this is called a dipole moment. So we draw arrows this way. And so this leaves this side of the molecule is positive, and this side of the molecule is negative. Now, there's a big argument in biology. They say that, oh, ionic bonds are weak bonds because they can be broken up in water. In actuality, that's not the case at all. Have you ever tried to melt salt? Anyone? No? I think you did a lab in pre-AP where you tried to heat salt. And did it go anywhere? No, you need to be like 900-something degrees to overcome this opposite attraction. These bonds are actually opposite attractions that are going on. It's not a sharing of electrons and orbitals. So, due to the fact that water has this dipole, it is capable of actually sneaking in and attracting the ions of the lattice of this we call this ion a lattice. Anytime you have an ionic compound, it's called a lattice. the opposite ends of the water are attracted to the ions in the lattice. So these ions ultimately are just as attracted to the different sides of water as they are to themselves, so the dissolving process happens. Now I want to go a step further with this and ask you, well, why does it happen? Yeah, the ions are attracted to the water, but they're just as attracted to each other, so why would it even happen? And it has to do with some other driving force in the universe. I'm going to see if y'all can try to remember. Think to thermodynamics, as you covered some of it in pre-AP. What drives the universe? Whoa, no, not Zoll. Close. Entropy. Entropy is a measure of what? Disorder. Okay, and I'm not going to quiz you on entropy right now, but the universe tends to disorder. So even though the salt is just as attracted to itself as it is to water, do you see how this on the right, after dissolution, is more disordered than on the left? Okay, so that's the ultimate thing driving this. So as long as there's no energy loss here through the switching of partners in charge going on, it's going to happen because it's an increase in entropy. So that's why dissolving happens. So what do you need to know about this? What do you have to do? You need to be able to draw a representation of ions in an ionic salt dissolved in water. You have to pay attention to the charge on the ions and make sure they're lined up appropriately with whatever side of water they need to be next to. So you can see here, this is a negatively charged ion, so the partial positive, the hydrogen side, is surrounding the ion. Versus here, we have a middle that's positive, so the waters are flipped. Okay? Got it? Any questions on that? All right, so practice drawing those. You will see those again. Next up, strong, weak, non. First off, what is an electrolyte? And you're going to have to write this down. What's an electrolyte? Well, I want the definition. Yeah, salt is an example. And a soluble salt is an example of an electrolyte. But what is an electrolyte? No? Yeah. Okay, something that splits up. Yes, something that splits up is an example of an electrolyte, but what makes a solution an electrolytic solution? What can it do? It conducts electricity. That's all it is. An electrolyte is a solution that conducts electricity. That's it. So when you hear, oh, you're having electrolytes because you're getting cramps, what's going on is you're ingesting these salty solutions, these ions that will go in and help mediate or facilitate stuff going on in your muscles with your potassium sodium channels and your nerves and all these different things going on. Okay? But by definition, an electrolyte is something that conducts electricity. So looking at that first picture there, that is a strong electrolyte. If you were to take a bulb that's attached to a battery there and stick it into an electrolytic solution that's strong, you would complete the circuit. Why is that? Because what, Mike? It conducts electricity because, why? What's in solution? Ions. Lots and lots of ions in solution allow for the movement of electrons, allows for the conduction of electricity. Okay? So what are some examples of things that could be strong electrolytes? We just said it, basically. Soluble salts. Not all salts are soluble. And what do I mean by salts? Let's ramp up that definition. What is a salt? An ionic compound. So I'm one of those pain in the butt people that when people say, oh, I'm going to put some salt on mine, I'm like, what kind of salt? I know they mean table salt, but you need to understand the term salt is referring to any ionic compound. Okay? Not all of them are soluble. There are a few solubility rules that you're going to be familiar with here in the next few days. Now, weak electrolyte. Oh, there's some other things that also will dissociate to make ions in solution. Who remembers from Chem 1? 100% dissociation. That should ring a bell. At home, they're all staring at me. All their eyes are forward on me, and no one has any idea. What? Nitrates are soluble. That's part of the soluble salt business. It's a different class of compounds entirely that sometimes it's 100% dissociated, sometimes they're not. Yes, strong acids and strong bases. Strong acids and bases are strong electrolytes. They will 100% dissociate in water, and you have a whole bunch of ions floating around. Usually it's going to be either the H plus or really it's the H3O plus floating around. What's floating around for bases? Not just OH. I don't know what OH is. OH minus. You think I'm splitting hairs by demanding that minus, but I'm not, because there's no such thing as OH. It's an OH minus. Okay. What are then some examples of weak electrolytes? Things that might not dissociate 100%, but still dissociate a little bit. Weak acids and bases. And I heard something that was interesting out there. Someone said, insoluble salts. That's actually a really, really good point. Insoluble salts, be them insoluble to our eyes, do dissolve a smidge, a little bitty bit. So they might make this little light bulb turn on a little bit. Some are so insoluble that it wouldn't at all, but I'm going to write some insoluble salts. And we're going to learn about this when we get to acid and base, about something called the KSP, and it's a measure basically of how much of a salt, an insoluble salt, will actually dissociate. And we'll talk about that. That's not until like January of 2014. Okay, so what's next here? A non-electrolyte. What things do not dissociate into ions at all? Exactly, covalent compounds. So give me some examples of covalent compounds. Methane, okay, that's a gas, so if we bubble it in water, it won't. What about some solids that you dissolve in water that are polar and dissolve in water but don't dissociate? Oh, please. How many of you had a soda in the last few days? Sugar, yeah. Okay, that's something that dissolves. Isn't water itself a covalent compound? So how come they yell at you to get out of the pool when the lightning comes? Because it's not pure water, not to mention the fact that the second you put your body in there, you're putting in impurities that could be ions and changing the conductivity of that solution. Okay? So, pure water, pure distilled water does not conduct electricity. Okay? All right. So what we're going to do now is move on to looking at writing equations to represent things that actually are electrolytes in solution in water. To do this first, we really need to remind ourselves about the acid and base strength. Acid, ooh, I'm doing acid in red and base in blue. Why would I do that? What kind of strip? What's it called? It's not just a litmus. Yeah, that's the color of litmus, right? Okay, so acids. Strong acids. There's a couple rules that that'll help you. The one big rule that supersedes every rule of all the rules is that carbon containing acids, who remembers what they are? Strong or weak? Weak. So any any acid that you come into connection with, that you happen to see that has a carbon in it, like acetic acid or carbonic acid or any weird organic acid that you don't even know the name of, they're going to be weak. Now, when you get to organic, I'm going to take it back. But that's way more specific than anything you're going to have to be familiar with, and that has to do with conjugates and all that mess. So any carbon-containing acid for now is weak. All right. Now there were a few lists. There's some strong acids you guys had to memorize last year, and I'm hoping that you'll just internalize them and not sit there and have to know this list. But first off, there's 3 strong binary acids: hydroiodic, hydrobromic. Why did I write them in this order? I write them in this order because how many of you guys learned I-bring clay for our new house when you did diatomics? Okay. Well, I figured out to say I-bring clay. It's just I-bring clay. Those are the strong 3 binary acids. All right. Any other binary acid is weak. You know, HF is one of them. HF always confuses people because they're like, well, that etches glass. Being strong in terms of H plus dissociation versus molarity and its molecular ability to affect things, they're totally independent. Okay, so HF, although it etches glass, it doesn't dissociate a whole heck of a lot into H plus and F minus. All right, ternary, there was a rule for this. Who remembers the rule? It has to do with the ratio of H's to O's. 2 or more O's than H's. I'll write it in black. 2 or more O's than H's. So for instance, if we have HNO2 versus H, uh-oh, my microphone just clicked. I hope it's still going. Yep, looks like it's still going. Okay. So, HNO2, does that have 2 or more O's than H's? No, that only has 1 more O than H, so that is not strong. HNO3, that's 2 more O's than H's, and it's 2 or more O's than H's. Okay, so just keep that in mind. And remember, if you've got a C in there and it's some long, crazy acid, don't sit there and try to count O's and H's. Okay, it's got a carbon, it's an organic acid, it's weak. Okay, our bases. The bases are pretty important. Remember, you told me earlier that hydroxide ions are what makes things bases. So our hydroxides that are going to be strong are the ones that are always soluble. So they're the group 1, and then the bottom 2 of group 2. We don't care about Ra because it's radioactive. When we say bottom 2, we're talking about Sr and Ba, strontium and barium. Group 1 and strontium and barium hydroxides are your strong ones. All the other hydroxides are going to be weak. They do not dissociate 100%. They dissociate a smidge, but not 100%. Okay. And then there's one very famous base that doesn't even have an OH in it, but it's the consummate weak base. When we talk about weak bases, everybody uses this as an example. Can anyone remember? Doesn't have an OH in it. Ammonia, very good. NH3. Not ammonium. Ammonia is weak. Now, in order for something to be a base, it has to have OH minus in solution. This doesn't have OH, so I'm going to show you why it is basic. Why does it make an OH? And that's because when it's put in water, we get a movement of a proton. We get a Laurie-Bronsted acid-base reaction. And again, that's going to be something we're going to study more later. But I do need you to know ammonia is weak, and it won't dissociate, it won't react 100% to form hydroxide ions. All right, so let's take all this now and translate over here to our first question. We're supposed to look at HClO4. What's that called? Perchloric acid. It's binary. We don't use the word hydrogen. List whether each of the following is a strong, weak, or non-electrolyte. So what is this one? It's a strong what? Strong acid, so is that a strong, weak, or non-electrolyte? Strong. So how does this dissociate in water? It's strong, so I'm going to get a one-direction arrow that indicates it goes to completion. Shoom. All the way. All of it splits up into ions. What ions does it split up into? Good. H plus plus ClO4 minus. Last period, I had people saying, O2 minus and Cl minus 1, and they were breaking up the polyatomics. You don't break up the polyatomics. Does anyone know how Cl and O and O and O are attached to each other? Those are covalently attached to each other. Okay? So there's water is not going to have the ability to get in there and split those apart. Water can only go in between ions because of the charge differential. All right? So since ClO4, any polyatomic, is covalently bonded to each other. You've drawn pictures where they're sharing electrons, right? So that means that they're not going to split those up. Now another way you can draw this or write an equation, any acid or base in a solution, you can always add water, and when you do that, it's the same exact equation. The same exact thing happens, except now the H donated to this water, and we're going to get H3O plus ClO4 minus. Folks, that's the exact same thing. When we see this and we see this, I want you to think they're the exact same thing, because they are. One's the hydrogen ion. Who remembers the name of this? Hydro... Thank you, hydronium. Hydronium ion, okay? All right, so let's look at this next thing. C6H12, strong, weak, or non? How about a non? What is this? This is not carbon. It's not an acid. What are y'all doing? It's not a base. How about a covalent compound, right? It's a covalent compound. And didn't you all tell me on the last slide covalent compounds were non-electrolytes? So we're not going to write the equation. So it's a non. Don't forget about those covalent compounds. Anything you'd name, I should have had you name it. What would you name that thing? Hexa? Carbon. There's actually a formal name, but through IUPAC, hexacarbon, carbon, dodecahydride. Okay? Well, because we're using prefixes like that, it's not. It's actually not. It's actually hexane, but we'll do organic stuff later. All right, what is this next one? What kind of base? It's a strong base. So is it a strong, weak, or non-electrolyte? Strong electrolyte. All right, how would this guy split up in water? So I'm drawing an arrow, full arrow completion, Li plus OH minus. I'm mentioning that because this next one, our arrows are going to be a little bit different. It does say if it's strong, write the dissociation equation, but I'm going to take you a step further, and I want you to write the dissociation equation if they're weak. So we already classified ammonia as what? A weak base, making it what kind of electrolyte? Weak. Since this is one of those special ones, if you see something and you're like, I can't make an OH in solution out of it, I can't make an H+, add it to water, okay? And so what we're going to do is we're going to do NH3 plus H2O. If I write it like this, maybe that'll help you see it. I'm going to draw a double-headed arrow because this is a reversible equation. And it doesn't 100% make ions. It'll go back and forth and back and forth, all right? So if I need to get OH out of this water, OH minus, what's left over? H plus, and that's what happens. Bases are proton acceptors, and so we get NH4 plus OH minus. This is what makes that basic. And because it's weak and it's going back and forth like that, it's not going to happen 100%. Yay? Good? Yay. All right, NaCl, what kind of compound is that? A salt. And it's specifically, you know this is soluble, right? I hope so. Have you ever swam in the ocean? Maybe? Has anyone been to the Dead Sea? Just curious. You have? I want to go there so bad. Did you go in? I know, but still. Burns? I know, I still though. It must be a weird sensation to get in the water. Did you just like pop right back up? I looked at the density of that water once because it's so concentrated. I want to say it was like a density of 11 or something, and water's normally a density of 1. Yeah. So what? I'm sure the water is evaporating to an extent because she said there's crystals of salt formed. I still want to go. I really, really want to go see it. All right. So anyway, when NaCl is dissolved in water, what does it split up into? 100%. What? Plus Cl minus, making this a strong electrolyte. All right. H, C2H3O2, what's that called? Acetic acid. Acetic acid is a weak acid because it contains a carbon. And then if it's a weak acid, what does it make it? A weak electrolyte. Do you want me to add this to water or not? It doesn't matter. No? Okay. H, C2, H3O2. So what ions do we dissociate to? Thank you. All right. And finally, we have ammonium chloride. We have 2 ions together making what kind of compound? Ionic, which is also known as a salt. So that is a salt. And I'll tell you now, all ammonium-containing salts are soluble. Okay, that's one of those solubility rules. So this is a soluble salt. Let me use a different color. Soluble salt. And since it's a soluble salt, it's going to dissociate 100% with an arrow going in one direction. And oh, what did I do wrong on the last problem? Arrows. It's not 100% dissociated because it's weak. I just caught that. All right, back to ammonium chloride. What does ammonium chloride break up into since it's ionic? Good. And there you have it. Those are the rules for the day. So what we're going to be doing next class, I'm really excited about it. I mean, not the test is Monday. Tuesday's a little lab thing, but Wednesday's class, we're going to introduce you to molarity. Most of you know it. Do a little bit of that. And then we're going to start the bullet lab. I just want to tell you about the bullet lab. It's so cool. You're going to get a bullet casing, and you're going to analyze it for the % of copper in it. And then from a list of manufacturers, you can verify who makes it. It's like CSI totally. And these are bullets that I actually used after I murdered multiple people. No, I'm kidding. I'm kidding. I went to this gun range, and I was like, hi, and it's all bam, bam in the background, and really loud, and I'm like jumping, all nervous, like I shouldn't have been there. And I walk in, and I guess the fear on my face made them all kind of laugh and go, can we help you? I'm like, hi, I'm a high school chemistry teacher, and I need some bullet casings. And the guy's like, why do you need bullet casings? We're going to analyze them for the % of copper and the brass. He's like, oh, okay, how many do you want? And so he went and collected them. And so there's like a mixture of them. I didn't have a gun. I actually talk all tough. I was so nervous in that place. Like, that's loud. And I was in another room. I wasn't even in the actual gun range part of it. So anyway, very excited about the bullet lab. It's going to be a lot of fun. And so your test is on Monday. This homework from tonight, re-download both of those calendars, is not due until the Wednesday of the new lecture day. And it does say that on the Unit 1 calendar. Okay? All right, that is all.